So our next speaker is Łukasz Michalak from Adam Mickiewicz University in Poznan, and his talk is titled Reeb graph invariants of Morse functions, manifolds, and groups. Please.
Thank you very much. First of all, I would like to thank the organizers for their effort and for the opportunity to give this talk. In the previous talk, they were considered Reeb graphs for algebraic domains, but here I will consider smooth manifolds of dimension at least 2, and the smooth functions with isolated critical points, so with finitely many of them by the compactness of the manifold. I especially focus on Morse functions, so functions which have non-degenerate critical points. And in 1946, French mathematician Georges Reeb and later also Alexandre Cronrod introduced the relation whose equivalence classes are connected components of the level set of the function. And the obtained quotient space we denote by R of f, and it is called the Reeb graph or Cronrod-Reeb graph of a function. And for such a function with isolated critical points, this is in fact a finite graph, so one-dimensional finite CW complex, and its vertices correspond to connected components of level sets containing critical points. Here we see a classical example of a height function on the torus and its Reeb graph, which has one cycle. For example, this red cylinder is contracted by the quotient map to this edge of the graph. And it should be noted that we can consider Reeb graphs for wider classes of functions. And for example, Psyche recently proved that if we consider function with infinitely many critical points, but with finitely many critical values, then also the Reeb graph is a finite graph. But Reeb graphs became more popular in the 90s, probably started by the paper of Shinagawa and collaborators, where Reeb graphs were proposed to use in computer graphics for morphing, coding, and comparing objects. And now they play a fundamental role in computational topology for shape analysis. And also the algorithmic version, the mapper, is a basic tool in topological data analysis, which was started by Singh, Pamoli, and Carson. But Reeb graphs have also many applications to pure mathematics. They can be used everywhere where we would like to compare functions. So they are used in the study of the space of Morse functions, Morse bot functions, in singularity theory, foliation theory, even in differential equations. We also showed with Václav Marzantowicz that they have some applications in geometry group theory, the study of epimorphism of free groups. But now I would like to focus on the question what Reeb graphs can say about a manifold itself, what topological properties of a manifold can be seen in Reeb graphs. So let us start with first basic property of Reeb graphs. It is the so-called good orientation of a graph. This orientation induced by a continuous function, which satisfies the following two conditions. First, it is strictly monotonic on the edges, and it has extrema exactly in the vertices of degree 1. And this orientation was described combinatorially by Charcot, and it is easy to see that any Reeb graph admits such a good orientation induced by a function to obtain by the quotient topology. And Charcot also showed that it is a specific orientation. There are graphs which do not admit it, as the one on the left. There are combinatorial issues which do not allow to construct such a function. But we add one edge for example, here, then such a graph can admit a good orientation. So this is one thing. The second second thing which describes graphs are its number of cycles, and it can we have some properties about this number of cycles from the following construction provided by Kaluba, Marzantowicz, and Silva. So for a given function with isolated critical points, we can construct a graph gamma of f and its embedding if a manifold such as the composition with the quotient map is the homotopy equivalence of graphs, and in fact it contracts the trees on critical levels to the points, and it is bijective on the rest of the edges. And so from this we obtain that the quotient map induces epimorphism on fundamental groups. The fundamental groups of a Reeb graph is the free group with of rank equal to the first Betti number of the Reeb graph. And so we obtain that this first Betti number of the Reeb graph, its cycle rank, is bounded by the corank of the fundamental group of the manifold, where the corank of the group G is the maximum rank of a free group onto which there is an epimorphism from a given group G. And the starting problem for my research was the following question: if we have a given manifold, which graph can be realized as the Reeb graph of a function, especially of a Morse function? So I would like to emphasize that we have a fixed manifold M, so it is a harder problem than if we would like to construct a manifold and a function. And realization can be up to value relation up to isomorphism of oriented graphs, and it is still unsolved for higher dimensional manifolds. And up to also can be this problem considered up to orientation preserving homeomorphism of graphs. So we ignore vertices of degree 2, and also up to homotopy equivalence. So we have seen that the Reeb graphs have two necessary conditions: a good orientation and its cycle rank, its Betti number not greater than the corank of the fundamental group. And summarizing the realization theorem for Reeb graphs, we see that these two conditions are in fact sufficient to construct a Morse function on a manifold whose Reeb graph is orientation preserving homomorphic to a given graph gamma. And we can provide a complete classification of Reeb graphs for of functions on surfaces for up to isomorphism for various classes of functions, but for high dimensional manifolds it is harder to do. And the idea of the proof is the following. First, we need to construct a Morse function whose Reeb graph is in the so-called initial form, as we see on the left. And then we introduce the modifications of Reeb graphs, which are realized by modifications of Morse functions. These modifications comes from Morse and Hendon theory, for example, rearrangement and cancellation theorems, but we also need to use some other surgery constructions to obtain more complicated modifications of Reeb graphs. But having these modifications, we combinatorially prove that any given graph gamma with good orientation can be obtained by using these modifications from the initial graph. So this is realization up to homomorphism of graphs. And recently Saeki provided a construction of a function whose Reeb graph is isomorphic to a given graph gamma, but the function has it has finitely many critical values, but it has infinitely many critical points. And in fact, these critical points form n-dimensional submanifolds. So these such functions do not reflect many topological properties of a manifold. And it can be seen also even for surfaces, because if you would like to realize a graph as the Reeb graph up to isomorphism, or as the Reeb graph of a Morse function, then, for example, for orientable surface of genus G, the number of vertices of degree 2 in the graph needs to satisfy the following inequality. So yeah, we cannot construct any graph up to as a Reeb graph up to isomorphism ignoring vertices of degree 2. So yeah, it is still open for high dimensional manifolds. So and in fact, the problem of calculating the number of degree 2 vertices in Reeb graphs is related to the other problem of finding an algorithmic method of calculating the Corank. It was proposed by many authors because this problem is related with the solving equations in free groups. And for example, Stallings proposed to use systems of hypersurfaces, so the systems of codimension 1 submanifolds with trivial normal boundaries, but we don't know of such a method. And yeah, but in fact, there is such an algorithmic method of computing the Corank. This is a method of the so-called Markkanin-Rasborov diagrams, and they allow us to describe the structure of the set of homomorphisms from a given group G to the free group. But in fact, they are hard to use in practice in particular situation. Yeah, yeah, it is hard to do it. So we can try to use Morse function as Reeb graph to solve this problem. And so the problem is how to find function whose Reeb graph has maximum possible cycle rank equal to the Corank of the fundamental group. And so the function we call maximal, and Ki is the number of critical points of index I of a simple Morse function. And we can relate the number of degree 2 vertices in the Reeb graph with the number of critical points and the cycle rank of the Reeb graph. And from this, we obtain some lower bands for the number of degree 2 vertices in Reeb graphs. The first one uses rank and Corank of fundamental group. The second one uses also homology group with ring coefficient R, and also the last inequality uses Lusternik-Schnirelmann category of a manifold. And these bounds are essentially different. And if we take a minimum on the left, we obtain the number delta 2 of them, the minimum number of vertices of degree 2 in Reeb graphs of simple Morse functions. Yeah, for surfaces, it is easy to compute. It is 0 for orientable surface of genus G and non-orientable of even genus. But for non-orientable surfaces of odd genus, this number is 1. We always have one vertex of degree 2 in Reeb graphs of simple Morse function. And yeah, and this number can be arbitrarily large even if we fix a dimension. So how to compute it? And let us see on the case of three-dimensional manifolds, and in this case, all these three bounds can be improved by the following one using Hegardt genus of a manifold. And in fact, if we assume that function has only two extrema, then the number of critical points of index 1 and 2 are equal and are bounded from below by the Hegardt genus. And yeah, a Morse function with minimum number of critical points is the one which has K1 equal to the Hegardt genus of the manifold. And the following proposition shows the equivalence of three conditions, which shows that the equality in this bound with heterogeneous is equivalent to the statement that we can find a maximal simple Morse function with minimum number of critical. And in fact, if we take any simple Morse function, any, but with a minimum number of vertices of degree 2 in a Reeb graph, then it is automatically maximal and has the minimum number of critical points. So the question is for which manifold we have equality in this bound and also in previous bounds. But let us focus on three manifolds and how to describe this number and or calculate it. And we can use the following methods from group presentations. Recall that we have a presentation of a group with n generators and n relators. Then its deficiency, the deficiency of a presentation is the difference, n minus m, number of generators minus number of relators. And the deficiency of a finitely presented group G is the maximum over deficiency for all presentations of a given group. And it is known that Epstein showed that for orientable closed free manifold, the deficiency of its group is always 0. And we introduce the following invariant omega of a presentation, which is the minimum number, such that in a given presentation, we can write first relator using first omega generators, second relator using omega plus 1 first generators, and so on. And this is then the omega invariant of a presentation, and for a given rank n, we can take a minimum over all omega numbers for all presentations of the same deficiency as G, and the rank equal to n. And also we can take the minimum overall. All ranks of presentations obtain the omega of G. And how it is related with Morse functions and Reeb graphs. It turns out that we consider simple Morse function on orientable free manifold with one minimum. Then omega k1 of the fundamental group of free manifold is bounded by k1 minus the first Betti number of the Reeb graph. And in particular, the minimum number of degree 2 vertices in the Reeb graphs of simple Morse function is not smaller than the twice of omega invariant of the fundamental group of a manifold. And for example, if we take a group G which is non-trivial, non-free, and torsion-free, then its omega invariant is at least 2. And so if we have a manifold with torsion-free fundamental group and with the difference between the heterogeneous and co-rank equal to 1, and heterogeneous at least 2, then this number of delta 2 of m is at least 4. And so we have no equality in the bound, dimension bound using heterogeneous, and so we cannot find a maximal Morse function with minimum number of critical points. And for example, it is the case for Heisenberg manifold, for which this number delta 2 of m is equal to 4. But yeah, there is no maximal Morse function with minimum number of critical points. So let us see on the non-trivial calculation of this invariant for circle bundles over a surface. These bundles are classified by the Euler number, is an integer, and the co-rank of such a circle bundle is equal to, or the group of the circle bundle is equal to G. And if the Euler class is different, it's not generator, not plus minus 1, then the heterogeneous is 2G plus 1. And in fact, we have equality in our bound. So it has nice properties. We can find maximal Morse function with minimum number of critical points. But the question is, what is when the Euler class is a generator? Then the heterogeneous is decreased by 1, it is 2G. And it is the presentation of the fundamental group of such a bundle. And we need to use the following theorem, which is called Freiheitssatz. It is from PhD dissertation of Wilhelm Magnus. And recall that word-eaten free group is cyclically reduced if it is reduced, and yeah, the product of the last and first letter is non-trivial. And this Freiheiser states that we have cyclically reduced word in a free group, which contains some generator, and every non-trivial element of its normal closure also contains this generator. And yeah, using this, we may show that the omega to G invariant of the fundamental group of the circle bundle is equal to G. It is maximal possible. Okay, I need to finish, so maybe I skip the sketch of the proof. But combining these facts, this inequality, and that for this manifold, such a manifold, we have 2G, omega 2G is equal to G, we obtain a corollary that any simple Morse function with minimum number of critical points has no cycles in its Reeb graph. Any Reeb graph is a tree, and it has 4G vertices of degree 2. But it turns out that if we increase the number of critical points by 2, so another first step with decreasing the number of critical points, then we can construct a simple Morse function, maximal Morse function, whose Reeb graph has cycle rank equal to the corank of the fundamental group, and in fact, then we obtain the minimum number of degree 2 vertices, which is equal to G plus 2. Okay, thank you.